So in this linear algebra course, we're going to be studying vector spaces. Basically, what you learn in any linear algebra class. Uh, the properties of vector spaces, the study of linear maps on finite dimensional vector spaces, and other stuff that will come along. And we're going to learn what these terms mean later on. But for now, we begin with this first section, which is Rn, or the reals, set to the reals to the n and the complex numbers. We're going to see what this means exactly. The reals to the n. This first chapter by defining what a complex number is. And a complex number is an ordered pair, AB, where these AB are both real numbers, and we write them as A plus BI. That's how we're going to define what a complex number is. Now in set notation, we can write this as C, and that C is equal to the set A plus BI as we write it, such that A and B are real numbers. That's how the set of complex numbers is going to be denoted. A single number will be A plus BI, and the set of complex numbers is denoted by this C. Just to point out really fast, if you haven't seen any videos from this channel, this green box here, the green box is always used for definitions. If you see a green box, it's because there's a definition, at least one definition there. In this case, it's the definition of a complex number. This yellow box is sometimes something you want to note, something, that either I want to point out or some properties that may be useful for later on. And then we're going to go over other colors as they come up. But anyway, as we move on, we have the complex numbers, and now we can define what addition and multiplication on these complex numbers is. So they're defined by A plus BI plus C plus DI. So here, this is addition. We have one complex number here. I'm going to just call it alpha. We have another complex number here. I'm going to call this one beta. So we have two complex numbers being added. And how you add these is you just add the corresponding components. So A plus C from over here, and then B plus D. We still do have an I, so we're going to keep the I out here. But that's just how we define addition on the complex numbers. I'm going to erase this so we can make more space, because we're going to define what multiplication is. And multiplication is defined like this. So what we do is multiply A times C. We have it right here. A times DI. You have it A times D, and then the I. BI times C. So we have BI times C, so BC, and then the I again out here. And finally, BI times DI, which, if you remember, we assumed that -1 was the square root of, I was the square root of -1. And if you remember for an algebra 1 or 2 in high school, I squared is just equal to -1. So if we multiply BI times DI, we get -1 times BD, which is why we're subtracting BD now. And that's how we multiply these. That's how multiplication is defined for the complex numbers. And again, I'm just going to erase so we can, for this stuff to come. And here, of course, all A, B, C, and D are real numbers by definition of complex number. Now we're going to go over, so this purple box up here that popped up means we're going to be going over an example now. So what if we had to evaluate these two complex numbers being multiplied? How does that work? Well, as we saw down here, we just follow these steps. And it shouldn't be hard to derive or if you remember, you don't have to remember how to multiply them. You can figure um, the multiplication out as long as you remember that we assume that I is equal to the square root of -1. So our multiplication comes out to this, following our steps, which then turns to this. We're just cleaning stuff up. And finally, it gives us -7 plus 22i. This is just an example of complex numbers being multiplied with each other. Not with each other, but a complex number being multiplied by another complex number. Okay, now this next blue box, dark blue, means theorem. That means we're going to have theorems come up. And these theorems are actually properties. So these properties we're going to go over here are properties of complex arithmetic. And if you've taken a class in modern algebra, or also known as abstract algebra, maybe you've seen these quite often. So first one, we have commutativity. We have a plus b is equal to b plus a. So it's commutative under addition, and over here it's multiplication. I said a plus b, but it's actually alpha plus beta. Not that it matters. Is equal to beta times alpha for all alpha, beta being complex numbers. So that's commutativity. Again, these are theorems, so there are proofs, but these shouldn't be too hard. You can do them. They're proven the same way you prove the real numbers, the properties of the real numbers. Next is associativity. If we have alpha plus beta in parentheses plus lambda, well, it's the same thing as the one from the other side. Same thing with multiplication. Again, this is a theorem, so there's a way to prove this. Should not be complicated. That's associativity. If you can guess what's next, it's going to be identities. So we have identities. Lambda plus 0 is equal to lambda. That's the additive identity and the multiplicative identity for the complex numbers. And that's where an alpha is a complex numbers, because we're dealing with complex numbers here. Next, we have the additive inverse. What does that mean? That means that for every complex number alpha, there exists another complex number beta, and it's unique, as it says here. There's only one, such that if you add them together, it will give you the additive identity, which is 0. Okay, we also have the multiplicative inverse. In this case, multiplicative inverse, just like the real numbers. Sorry. So if you have a complex number, sorry, I shouldn't have said just like the real numbers. Here, for an alpha being a complex number, as long as it's not 0, there exists a unique complex number beta, such that if you multiply them, you'll get exactly 1. And there's always one, and there exists, it's unique. That's a big word there. Let me erase it so you can see it. So it's a unique complex number. And the last property is a distributive property. Again, you should have maybe seen this in high school, but maybe not defined formally. Here, again, there's a proof for this distributive property for these complex numbers lambda, alpha, and beta. And to not leave you in the dark completely, we're going to go ahead and prove one of these. And for proof, we're going to use a different color. I'm going to show you over here. I'm going to show you that this holds true. That complex numbers under multiplication are commutative. So we're asked to show this statement is true for all alpha, beta complex numbers, being complex numbers. So it's pretty straightforward. We start with the first complex number, alpha, next complex number, beta. Of course, by definition, having A, B, C, D be real numbers. And we just pretty much multiply them out. Alpha times beta, we have here. Again, following our steps from multiplication from the yellow box, we get that we have this product, again, two terms. And now if we multiply beta times alpha, here's beta, here's alpha. If we multiply those two out, we get this product. Now this product and this one don't quite exactly look the same. But because real numbers are commutative, we can switch terms around. And again, real numbers are commutative with both addition and multiplication. So that's why we can switch those around and make it so that they do look the same. What does that tell us? That tells us that therefore alpha times beta is equal to beta times alpha. Now we're going to define, we defined addition and multiplication here. Now we're going to define something else. We're going to define subtraction and division for complex numbers. So again, we let alpha and beta be complex numbers. And subtraction on the complex numbers is defined just pretty similar or almost identically to the real numbers. Is beta minus alpha is the same thing, or is equal to actually, beta plus negative alpha. And division, also like the real numbers, is defined as beta over alpha is the same as beta times 1 over alpha. So we define these for the complex numbers. So from this point on, we're going to use a notation F. And again, as it says here, it stands for either the reals or the complex numbers. And F here stands for a field. If you've taken abstract algebra, you should know that the real numbers and the complex numbers, actually, sorry, well, yes, they're both fields, with the reals being a totally ordered field. And that's why we have that F. And then a little just things to note is that if we have alpha being an element of the either field and m a positive integer, we defined a alpha to the m to denote the product of alpha with itself m times. So just as your intuition tells you, probably you're not wrong. That's how you've seen it before in high school and college. That's how we defined this exponent m. Also, these properties don't show the proof, but they shouldn't be hard to verify. So I'm going to just let you pause for a few seconds, just verify that before moving on, nothing too complicated. And now we're going to define what a list and length are. So suppose n is a non-negative integer. A list of length n is an ordered collection of n elements. And here I put parentheses because hey, they might be numbers, they might be other lists, or maybe even more abstract entities. But these lists are separated by commas and surrounded by parentheses. So a list of length n looks like this down here. So this is a list because there's x1, comma x2, comma all the way to xn because it's of length xn. And again, we have a parentheses just as it shows right here. That's our list of length n. So to help you visualize a bit better, a list of length 2 is given right here up above. We have x and y. That's length 2, and they're both real numbers. This visually, do you know what R2 looks like visually? We're about to see it. Over here we have a list of length 3, x, y, z. Again, they're all real numbers. And this is R3 because our list is of length 3. Now visually, these spaces look like what? Well, this is a Euclidean plane. This is what R2 looks like right here. And on the right, we have R3, x, y, z axes, I should say. That's what R3 and R2 look like. So we can have a list of length, well, n, it doesn't really matter as long as it's a non-negative integer. We can have a list of length 50, of a million, so on and so forth. It doesn't just have to be 2 and 3. But this is what lists are. My question is, do you think there's a difference between sets and lists? Well, let's find out. Here we have the ordered pair 5, 3, and over here we have the ordered pair 3, 5. They're both lists, but are those two lists the same? Well, if you look at a Euclidean plane and you graph those 2 points, are they going to be the same point? No. What about these sets though? 3, 5 and 5, 3. Are those the same set? Yes. And list, order matters, right? That's why when you hear ordered pair for R2, they include the word ordered. Same thing if we were to have the list 4, 4, the ordered pair, and the ordered triple 4, 4, 4. They're both lists, but are they the same? Well, no. One is a list of length 2, and the other one's a list of length 3. But what about the sets? If you include an element twice in a set, well, it's just like having it once, right? Repetition doesn't really change things with sets. So sets 4, 4 and 4, 4, 4 are exactly the same. These are the same. This one they're the same as a set, just 4. So that's a difference. There's a difference between lists and sets. Don't confuse them. They're not the same thing. Next, we're going to define what f to the n means. I usually just call it fn. So fn is a set of all lists of length n of elements of f. So it's exactly what you probably think, what your intuition tells you. Any elements in the set fn is a list of length n, right? So x1, x2, so on and so forth, all the way to xn. Oh, sorry, it's a list. Shouldn't have included that bracket. So that's simply what fn is. And now we have an example. So we have C4. It's the set of all lists of 4 complex numbers. So how does that look like in set notation? How could I describe C4 in set notation? Well, the way I describe it is like this. Z1, Z2, Z3, Z4, where those Z's are complex numbers. And it's lists of, well, yeah, of that form, of all of them, of all lists of length 4. That's all this means. Finally, I have the question, how does R4 look? Can you visualize that? Or can you visualize C6? Because up in the top right, we visualized R2 and R3, but not necessarily R4 and C6. So can you imagine what those look like? So the answer, if you're human, probably not then. If you're human, the answer is probably not. You can't visualize them. If n is greater than or equal to 4, we really can't visualize it, not as a physical object. So we're going to define what addition in fn means, meaning what if we add 2 lists together? Well, this here, just like the complex numbers, you add corresponding coordinates. That's all it is. x1 you add to y1, and all the way x2 to y2, all the way to xn plus yn. That's all that is. That's how you add list in fn. So I have a neat theorem. It's quite simple, it's straightforward. If x and y are elements of Fn, then x plus y is equal to y plus x. Here, before I go on, x and y don't necessarily just represent numbers here, right? Because they're elements of Fn. And Fn is what? Well, Fn, as we saw in the last slide, is a set of all lists of length n. So x here is a list, x1 all the way to xn. And y here is also a list, y1 all the way to yn. They're not just numbers, they're lists. And again, these variables over here, lists as well. But since we already defined addition in that green box, it shouldn't be hard to add these two lists together and see if, or show that our theorem holds or is true. So x plus y, those two lists added together, is equal to y plus x, meaning that these two lists, addition, is commutative in Fn. So proof, again, proof is light blue, theorem is darker blue. Proof. Suppose x is equal to, well, the list, x1 all the way to xn, as I had just stated, and y is equal to this list, y1 all the way to yn. What does this mean? Well, this means that we can just add them now. Looks exactly like this, adding the two lists together. How do we add lists? We add the corresponding coordinates. And these coordinates, because these coordinates are either complex or real numbers, now we know that they are commutative. So what can we do? We can flip them. x1 plus y1 is the same thing as y1 plus x1. And we flip all of them like that. So we have all the way to yn plus xn. And what does that equal to? Well, that just equals to the list of y plus the list of x. And that equals to y plus x. So this showed that addition is indeed commutative in Fn. Here, 0 denotes the list of length n whose coordinates are all 0. So this right here represents a list, and these zeros right here represent real or complex numbers. Or complex numbers. Those zeros are not the same. One's a list, one's a number. But that's how we denote 0 for lists. It's just a list of all zeros. And I'm going to erase this, just have more space. We're going to have a few drawings here. So before we move on to the drawings, we have that 0 is the additive identity of Fn. And you can verify this on your own. You can add a list x plus the list of 0 and see that it just equals the list x for all x in Fn. So that shows that 0 is the additive identity. But again, right here, x and 0 are not numbers. They are both lists. Right? Because why? Because 0 and x are both an element of Fn. Okay, so I just answered your question. Is 0 here, is the 0 here the number 0 or the list 0? Well, in this case, it is the list. In the case above, here, they are numbers. Okay, now to go to the visuals. We know that a typical element of R2 is a point, right? An ordered pair, x1, x2. Sometimes you know them as x comma y. In this case, it's x1 comma x2. And that point, we have it right here. Now, when you see an arrow, we're going to call that something. We call that a vector, right? And a vector is just an arrow of some length starting at the origin, ending at that point, at that ordered pair. This is an R2. So that's what a vector is here. Now these two vectors, well, this one moved down, right? Maybe to the side as well. But these two vectors are essentially the same. This one may have started at the origin and then ended up over here. But this one is also of the same length, just shifted down. So these are essentially the same vector. And we think of these vectors again in R2 as arrows. And we can move an arrow parallel to itself without changing its length or its direction. And really just still think of it as the same vector. And with this viewpoint, we gain better understanding by dispensing with the coordinate axes and well, such explicit coordinates, and just think of vectors as they're shown down here without the plane. Next visual is this visual down here. If we started at the origin here and went to this point here with the vector x, and then starting from this, or I shouldn't say new origin, but now starting from here, we follow the vector y, we would end up at this point. How else could we get to that point? Well, by starting at the origin and just going straight to that point. And that is the addition of vectors. X plus y would be this vector here. So this is the sum of two vectors in R2. And remember, in R2, it's really helpful because we can visualize it. But although we can't draw good pictures in high dimensional spaces, we use these ideas to show certain properties in higher dimensional spaces. Last but not least, I have a question. What do you think is the relationship between these two vectors, x and this one that looks like negative x? What's the relationship between these two vectors? Well, they are the additive inverse of each other. So for x in Fn, again, x is a list here, the additive inverse is denoted by negative x. And as you know, the additive inverse should give us the additive identity, 0, when added with each other. So those two are additive inverse. And it gives us 0, our additive identity. So we can write, in other words, that negative x here is the list negative x1 all the way to negative xn. Why? Because when we add these two lists, or actually subtract them, sorry, I should write it as when we add these two lists, we get x1 plus negative x1, so on and so forth, all the way to xn plus, let's write this like this, negative xn. And well, this just equals 0, 0, so on and so forth, which gives us our 0 list, or our additive identity in Fn. So if you want to pause, I'm just going to erase this really fast if you want to copy it down or try it yourself, just so we have space for just the last things to come. Okay, I guess I'll just leave it like that. And finally, the product, we can find a way to define, right? The product of lists, but mathematicians in their experience say that it hasn't really been helpful. Instead, there's another product that is of much more help in linear algebra, and that's known as scalar multiplication. I didn't quite write it down here, so I'll write it down here, right here. This is scalar multiplication. And what does this mean? Maybe you've heard it in a physics class you've taken. But if we have a number lambda, and a vector or a list in Fn, the product is computed by multiplying each coordinate of the vector by that number lambda. So again, if you have this right here, lambda times this list, you just multiply each coordinate in that list by lambda. That's how we do scalar multiplications. And here, finally, it tells us that lambda here is a number, right? Because it's just an element of f. So it can be a real complex number, either one of those. But over here, this is a list because it's an element of fn. So we multiply lambda, a number, or I should write, we multiply a number times a list. I'm just going to erase stuff too, so it doesn't look as messy, and to make a bit of space. Last thing is if we have this right here, this vector x, our original vector, question is, what is lambda for each of these cases? Well, in this case, there's a lambda times 1 because it just equals x. Over here, it gets compressed by what factor? By a scale of 1/2. So here it's lambda times our vector x. And lambda is 1/2. So here it's 1/2 is equal to lambda. Over here, lambda is equal to -3/2. Notice how now it's looking in the opposite direction because we have negative. -3/2. It stretched it by a factor of 1.5 and turned it in the opposite direction because lambda was negative. And that's all there is to, or for now, for scalar multiplication.